Welcome to the DRCU as a dynamic reactive compensation unit demo by Delving Research and Development Private Limited. Today, we'll show you how our cutting-edge solution can revolutionize energy management. This is our advanced online monitoring hardware components ensure precise control and monitoring of your electrical infrastructure. This is our 4-step capacitor bank, which can be expanded to up to 12 steps.
This is a connection diagram of the DRCU unit installed in the industry with a 4-step capacitor panel. CT is connected to the EB power supply as shown here. Clamp-type CT is used since it is an indoor application. DRCU unit is like a load, so the CT should be connected in which wire overall load connected. Here you can see CT has connected in the EB side. From CT to wires S1 and S2 has come as output, which is connected to DRCU unit for current measurement. The power supply for the DRCU unit and capacitor panel is taken from the load point. If we connect like this only, we can see the overall amps and power factor improvement. Similar to the industry connection diagram, here is the DRCU unit connection diagram for installation in a transformer with a 6-step capacitor panel. The CT is linked on the secondary side, LV side, of the transformer using a mold CT for outdoor use. The DRCU unit, functioning like a load, requires the CT to be connected where the total load is linked. In this setup, the CT is connected to the LV side. Two wires, S1 and S2 emerge from the CT as outputs, connecting to the DRCU unit for current measurement. Power for the DRCU unit and capacitor panel is sourced from the load point. This configuration enables an overall enhancement in amps and power factor. Here you can carefully observe and analyze the seamless integration of the dynamic reactive capacitor unit, DRCU, into the industrial setting. The prominent display vividly showcases essential metrics such as voltage, current, power factor, and angle values. Through meticulous computations, the DRCU aptly determines the necessary capacitor for the specific load, strategically incorporating capacitors one after the other to dynamically offset reactive power demands. Noteworthy enhancements were witnessed in the power factor, surging impressively from 0.7 to a commendable 0.97 by employing a sophisticated 4-step capacitor unit at the powerhouse complemented by an additional 5-step configuration at the load endpoint. A robust 40 kVAr capacitor bank stood tall, primed to support a 112 kilowatts load efficiently. Moreover, a fail-safe mechanism is in place to promptly deactivate the capacitor in case of predefined aberrant conditions in the rated voltage and current, ensuring operational integrity in all scenarios. You can see real-time data such as active devices, inactive devices, harmonics for voltage and current, load active hours and load inactive hours for selected devices, total inject kVAr, average power factor R, and maximum demand in kW. Also, it contains the total consumed unit with import and export for kWh and kVH. And also, you can see the individual steps with capacitor rating, active hour, and total injected kVAr for how much are we injecting for reactive compensation. Charts displaying data on voltage, current, power factor, capacitor required, inject kVAr analysis trend, energy consumption, inject kVAr analysis trend, time of day, phase angle, temperature, abnormality log, capacitor log, and energy report. The dashboard seems to provide a comprehensive overview of energy-related metrics and data visualization for monitoring and analysis purposes.